I have to ask about beautiful artificial life systems or evolutionary computation systems. Cellular Automata to me, I remember it was is a game changer for me early on in life when I saw Conway's Game of Life, who recently passed away, unfortunately. It's beautiful
Yeah.
how much complexity can emerge from such simple rules. I just don't somehow that simplicity is such a powerful illustration and also humbling because it feels like I personally, from my perspective, understand almost nothing about this world because like my intuition fails completely how complexity can emerge from such simplicity. Like my intuition fails, I think, is the biggest problem I have. Do you find systems like that beautiful? Is there do you think about cellular automata because cellular automata don't really have and many other artificial life systems don't necessarily have an objective. Maybe that's a wrong way to say it. It's almost like it's just evolving and creating.
Yeah.
And there's not even a good definition of what it means to create something complex and interesting and surprising. All those words that you said. Is there some of those systems that you find beautiful?
Yeah. And similarly, evolution does not have a goal. It is responding to current situation, and survival then it creates more complexity, and therefore we have something that we perceive as progress. But that's not what evolution is inherently set to do. And yeah, that's really fascinating. How a simple set of rules or simple mappings can from such simple mappings complexity can emerge. So it's a question of emergence and self-organization. And the Game of Life is one of the simplest ones and very visual, and therefore it drives home the point that it's possible that nonlinear interactions and this kinds of complexity can emerge from them. And biology and evolution is along the same lines. We have simple representations. DNA, if you really think of it, it's not that complex. There's a long sequence of them. There's lots of them, but it's a very simple representation. And similar with evolutionary computation, whatever string or tree representation we have and the operations, the amount of code that's required to manipulate those is really, really little. And of course, Game of Life, even less. So how complexity emerges from such simple principles, that's absolutely fascinating. The challenge is to be able to control it and guide it and direct it so that it becomes useful. And like Game of Life is fascinating to look at, and evolution, all the forms that come out is fascinating. But can we actually make it useful for us?
And efficient, because if you actually think about each of the cells in the Game of Life as a living organism, there's a lot of death that has to happen to create anything interesting.
Yeah.
And so I guess the questions for us humans that are mortal and then life ends quickly, we want to kind of hurry up and make sure we make sure we take evolution, the trajectory that is a little bit more efficient than the alternatives.
Yeah. And that touches upon something we talked about earlier, that evolution competition is very impatient.
Yeah.
We have a goal, we want it right away.
Yeah.
This biology has a lot of time and deep time and weak pressure and large populations. One great example of this is the novelty search. So evolutionary computation, where you don't actually specify a fitness goal, something that is your actual thing that you want, but you just reward solutions that are different from what you've seen before.
Yeah.
Nothing else.
Yeah.
And you know what? You actually discover things that are interesting and useful that way. Ken Stanley and Joe Lehman did this one study where they actually tried to evolve walking behavior on robots. And that's actually, we talked about earlier, where your robot actually failed in all kinds of ways and eventually discovered something that was very efficient walk. And it was because they rewarded things that were different that you were able to discover something. And I think that this is crucial because in order to be really different from what you already have, you have to utilize what is there in a domain to create something really different. So you have encoded the fundamentals of your world, and then you make changes to those fundamentals, you get further away. So that's probably what's happening in these systems of emergence, that fundamentals are there. And when you follow those fundamentals, you get into points, and some of those are actually interesting and useful. Now, even in that robotic walker simulation, there was a large set of garbage. But among them, there were some of these, gems. And then those are the ones that somehow you have to outside recognize and make useful. But these kind of productive systems, if you code them the right kind of principles, I think that they that encode the structure of the domain, then you will get to these solutions and these discoveries.
I think one of the most beautiful mathematical objects that at least today seems to be understudied or under talked about is cellular automata. What lessons do you draw from sort of the game of life or cellular automata, where you start with the simple rules, just like you're describing with the universe, and somehow complexity emerges? Do you feel like you have an intuitive grasp on the fascinating behavior of such systems, where some, like you said, some chaotic behavior could happen, some complexity could emerge, it could die out in some very rigid structures? Do you have a sense about cellular automata that somehow transfers maybe to the bigger questions of our universe?
Yeah, the cellular automata, and especially the Conway's game of life, is really great because these rules are so simple. You can explain it to every child, and even by hand you can simulate a little bit, and you see these beautiful patterns emerge. And people have proven, that it's even Turing complete. You cannot just use a computer to simulate game of life, but you can also use game of life to simulate any computer. That is truly amazing. And it's the prime example probably to demonstrate that very simple rules can lead to very rich phenomena. And people, sometimes, how is chemistry and biology so rich? I mean, this can't be based on simple rules, yeah? But no, we know quantum electrodynamics describes all of chemistry. And we come later back to that. I claim intelligence can be explained or described in one single equation, this very rich phenomenon. You asked also about whether, I understand this phenomenon, and it's probably not. And there's this saying, you never understand really things, you just get used to them. And I think I got pretty used to cellular automata. So you believe that you understand now why this phenomenon happens. But I give you a different example. I didn't play too much this Conway's game of life, but a little bit more with fractals and with the Mandelbrot set. These beautiful, patterns. Just look Mandelbrot set. And well, when the computers were really slow and I just had a black and white monitor, and I programmed my own programs in assembler to.
Assembler, wow. Wow, you're legit.
To get these fractals on the screen, and I was mesmerized. And much later, so I returned to this, every couple of years, and then I tried to understand what is going on. And you can understand a little bit, so I tried to derive the locations. There are these circles and the apple shape, and then you have smaller Mandelbrot sets recursively in this set. And there's a way to mathematically, by solving high order polynomials, to figure out where these centers are and what size they are approximately. And by sort of mathematically approaching this problem, you slowly get a feeling of why things are like they are. And that sort of is first step to understanding why this rich phenomena.
Do you think it's possible? What's your intuition? Do you think it's possible to reverse engineer and find the short program that generated these fractals, sort of by looking at the fractals?
Well, in principle, yes. Yeah. So, in principle, what you can do is you take any data set. You take these fractals, or you take whatever your data set, whatever you have. Say a picture of Conway's game of life, and you run through all programs. You take a program of size 1, 2, 3, 4, and all these programs, run them all in parallel in so-called dovetailing fashion. Give them computational resources, first one 50%, second one half resources, and so on, and let them run. Wait until they halt, give an output, compare it to your data, and if some of these programs produce the correct data, then you stop, and then you have already some program. It may be a long program because it's faster. And then you continue, and you get shorter and shorter programs until you eventually find the shortest program The interesting thing, you can never know whether it's the shortest program, because there could be an even shorter program which is just even slower, and you just have to wait, yeah? But asymptotically, and actually after finite time, you have the shortest program. So this is a theoretical but completely impractical way of finding the underlying structure in every data set, and that is what Solomon induction does and Kolmogorov complexity. In practice, of course, we have to approach the problem more intelligently. And then if you take resource limitations into account, there's, for instance, the field of pseudo-random numbers, yeah, and these are random numbers, so these are deterministic sequences, but no algorithm which is fast means runs in polynomial time, can detect that it's actually deterministic. So we can produce interesting, I mean, random numbers maybe not that interesting, but just an example. We can produce complex looking data, and we can then prove that no fast algorithm can detect the underlying pattern.
Which is, unfortunately, that's a big challenge for our search for simple programs in the space of artificial intelligence, perhaps.
Yes, it definitely is for artificial intelligence, and it's quite surprising that it's, I can't say easy. I mean, physicists worked really hard to find these theories, but apparently it was possible for human minds to find these simple rules in the universe. It could have been different, right?
It could have been different. It's awe-inspiring. There's a guy named Stephen Wolfram. Mm-hmm. There's a concept called cellular automata. So there's some mysteries in these systems that are computational in nature that have maybe echoes of the kind of mysteries we should need to solve to understand what is life. Mm-hmm. So if we could take a computational view of things, do you think there's something compelling to reducing everything down to computation, like the universe is computation, and then trying to understand life? So throw away the biology, throw away the chemistry, throw away even the physics that you learn in undergrad and graduate school, and more look at these simple little systems, whether it's cellular automata or whatever the heck kind of computational systems that operate on simple local rules and then create complexity as they evolve. Is it at all, do you think, productive to focus on those kinds of systems to get an inkling of what is life? And if it is, do you think it's possible to come up with some kind of laws and principles about what makes life in those computational systems?
So I like cellular automata. I think they're good toy models. But mostly like where I've thought about them and used them is to actually, let's say, poke at sort of the current conceptual framework that we have and see where the flaws are. So I think like the part that you're talking about that people find intriguing is that if you have like a fairly simple rule and you specify some initial condition and you run that rule on that initial condition, you could get really complex patterns emerging. Yeah. And ooh, doesn't that look lifelike? Yeah. Yeah.
Well, it's like really surprising, isn't it?
It is really surprising, and they're beautiful. And I think they have a lot of nice features associated to them. I think the things that I find, so I do think as a proof of principle that you can get complex things emerging from simple rules. They're great. As a sort of proof of principle about some of the ways that we might think of computation as being sort of a fundamental principle for dynamical systems and maybe the evolution of the universe as a whole, they're a great model system. As an explanatory framework for life, I think they're a bit problematic for the same reason that the laws of physics are a bit problematic. And the clearest way I can articulate that is like cellular automata are actually cast in sort of a conceptual framework for how the universe should be described that goes all the way back to Newton, in fact, with this idea that we can have a fixed law of motion, which exists sort of, it's given to you. The great programmer in the sky gave you this equation or this rule, and then you just run with it. And the rule doesn't have, so a good feature of the rule is it doesn't have specified in the rule information about the patterns it generates. So you wouldn't want, for example, my cup or my water bottle or, me sitting here to be specified in the laws of physics. That would be ridiculous because it wouldn't be a very simple explanation of all the things happening. It'd have to explain everything. So, and Cellular Automata have that feature, and the laws of physics have that feature. But you also need to specify the initial condition. And it basically means that everything that happens is sort of a consequence of that initial condition. And I think this kind of framework is just not the right one for biology. And part of the way that it's easiest to see this is a lot of people talk about self-reference being important in life. The fact that like the genome has information encoded in it, that information gets read out. It specifies something about the architecture of a cell. The architecture of the cell includes the genome. So the genome has basically self-referential information. Self-reference obviously comes up in computation a lot because it's kind of foundational to Turing's work and what Gödel did with the incompleteness theorems and things. So there's a lot of parallels there, and people have talked about that.
So in 2002, you published A New Kind of Science, to which, sort of on a personal level, I can credit my love for cellular automata and computation in general. I think a lot of others can as well. Can you briefly describe the vision, the hope, the main idea presented in this 1,200-page book?
Sure. Although it took 1,200 pages to say in the book. So no, the real idea, it's kind of a good way to get into it is to look at sort of the arc of history and to look at what's happened in kind of the development of science. I mean, there was this sort of big idea in science about 300 years ago that was, let's use mathematical equations to try and describe things in the world. Let's use sort of the formal idea of mathematical equations to describe what might be happening in the world, rather than, for example, just using sort of logical augmentation and so on. Let's have a formal theory about that. And so there'd been this 300-year run of using mathematical equations to describe the natural world, which had worked pretty well. But I got interested in how one could generalize that notion. There is a formal theory, there are definite rules, but what structure could those rules have? And so what I got interested in was, let's generalize beyond the sort of purely mathematical rules. And we now have this sort of notion of programming and computing and so on. Let's use the kinds of rules that can be embodied in programs as a sort of generalization of the ones that can exist in mathematics as a way to describe the world. And so my kind of favorite version of these kinds of simple rules are these things called cellular automata. And so typical case.
So wait, what are cellular automata?
Fair enough. So typical case of a cellular automaton, it's an array of cells. It's just a line of discrete cells. Each cell is either black or white. And in a series of steps that you can represent as lines going down a page, you're updating the color of each cell according to a rule that depends on the color of the cell above it and to its left and right. So it's really simple. So a thing might be, if the cell and its right neighbor are not the same, or the cell on the left is black or something, then make it black on the next step, and if not, make it white. Typical rule. That rule, I'm not sure I said it exactly right, but a rule very much like what I just said, has the feature that if you started off from just one black cell at the top, it makes this extremely complicated pattern. So some rules, you get a very simple pattern. Some rules, the rule is simple, you start them off from a sort of simple seed, you just get this very simple pattern. But other rules, and this was the big surprise when I started actually just doing the simple computer experiments to find out what happens, is that they produce very complicated patterns of behavior. So for example, this Rule 30 rule has the feature you started off from just one black cell at the top, makes this very random pattern. If you look like at the center column of cells, you get a series of values, it goes black, white, black, black, whatever it is. That sequence seems for all practical purposes random. So it's kind of like in math, you compute the digits of pi, 3.1415926, whatever. Those digits, once computed, I mean, the scheme for computing pi, it's the ratio of the circumference to diameter of a circle, very well defined. But yet, when you are, once you've generated those digits, they seem for all practical purposes completely random. And so it is with Rule 30, that even though the rule is very simple, much simpler, much more sort of computationally obvious than the rule for generating the digits of pi, even with a rule that simple, you're still generating immensely complicated behavior.
Yeah, so if we could just pause on that. I think you probably said it and looked at it so long you forgot the magic of it, or perhaps you don't. You still feel the magic. But to me, if you've never seen sort of, I would say, what is it, a one-dimensional, essentially, cellular automata, right? And you were to guess what you would see if you have some sort of cells that only respond to its neighbors.
Right.
If you were to guess what kind of things you would see, like my initial guess, like even when I first like opened your book, A New Kind of Science, right? My initial guess is you would see, I mean, it would be very simple stuff.
Right.
Like, and I think it's a magical experience to realize the kind of complexity. You mentioned Rule 30. Still your favorite cellular automaton?
Still my favorite rule, yes.
You get complexity, immense complexity. You get arbitrary complexity.
Yes.
And when you say randomness down middle column, that's just like one cool way to say that there's incredible complexity. And that's that's a magical idea. However you start to interpret it, all the reducibility discussions, all that, but it's just, I think that has profound philosophical kind of notions around it too. It's not just,
oh yeah,
I mean, it's transformational about how you see the world. I think for me, it was transformational. I don't know, we can have all kinds of discussions about computation and so on, but just, I sometimes think if I were on a desert island and was, I don't know, maybe with some psychedelics or something, but if I had to take one book, I mean, New Kind of Science would be it, because you can just enjoy that notion. For some reason, it's a deeply profound notion, at least to me.
I find it that way. Yeah. I mean, look, it was a very intuition breaking thing to discover. I mean, it's kind of like, you point the computational telescope out there and suddenly you see, I don't know, in the past, it's kind of like, moons of Jupiter or something, but suddenly you see something that's kind of very unexpected. And Rule 30 was very unexpected for me. And the big challenge at a personal level was to not ignore it. I mean, people, in other words, you might say,
it's a bug. What would you say? Yeah. What would you
say?
I
mean,
what are we looking at, by the way?
Well, I was just generating here. I'll actually generate a Rule 30 pattern. So that's the rule for Rule 30. And it says, for example, here, if you have a black cell in the middle and a black cell to the left and a white cell to the right, then the cell on the next step will be white. And so here's the actual pattern that you get, starting off from a single black cell at the top there. Then
that's the initial state, initial condition.
That's the initial thing. You just start off from that, and then you're going down the page, and at every step, you're just applying this rule to find out the new value that you get. And so you might think, rule that simple, you got to get there's got to be some trace of that simplicity here. Okay, we'll run it, let's say, for 400 steps. That's what it does. It's kind of aliasing a bit on the screen there, but you can see there's a little bit of regularity over on the left. Mm-hmm. But there's a lot of stuff here that just looks very complicated, very random. And that's a big sort of was a big shock to my intuition, at least, that's possible.
The mind immediately starts, is there a pattern? There must be a repetitive pattern.
Yeah,
there must be. That's where the mind goes.
So indeed, that's what I thought at first. And I thought, well, this is kind of interesting, but, if we run it long enough, we'll see, something will resolve into something simple. And, I did all kinds of analysis of using mathematics, statistics, cryptography, whatever, to try and crack it. And I never succeeded. And after I hadn't succeeded for a while, I started thinking maybe there's a real phenomenon here that is the reason I'm not succeeding. Maybe, the thing that for me was sort of a motivating factor was looking at the natural world and seeing all this complexity that exists in the natural world. The question is, where does it come from? What secret does nature have that lets it make all this complexity that we humans, when we engineer things, typically are not making? We're typically making things that at least look quite simple to us. And so the shock here was, even from something very simple, you're making something that complex. Maybe this is getting at sort of the secret that nature has that allows it to make really complex things, even though its underlying rules may not be that complex.
How did it make you feel? If we look at the Newton apple, was there a, you took a walk and something, it profoundly hit you, or was this a gradual thing? A lobster being boiled.
The truth of every sort of science discovery is it's not that gradual. I mean, I happen to be interested in scientific biography kinds of things. And so I've tried to track down, how did people come to figure out this or that thing? And there's always a long kind of sort of preparatory, there's a need to be prepared in a mindset in which it's possible to see something. I mean, in the case of Rule 30, I was around June 1st, 1984, was a kind of a silly story in some ways. I finally had a high-resolution laser printer. So I thought, I'm going to generate a bunch of pictures of these cellular automata. And I generate this one, and I was on some plane flight to Europe, and I have this with me, and it's like, I really should try to understand this. And this is really, I really don't understand what's going on. And that was kind of the, slowly trying to see what was happening. It was depressingly unsudden, so to speak, in the sense that a lot of these ideas, like principle of computational equivalence, for example, I thought, well, that's a possible thing. I didn't know if it's correct. Still don't know for sure that it's correct. But it's sort of a gradual thing that these things gradually kind of seem more important than one thought. I mean, I think the whole idea of studying the computational universe of simple programs, it took me probably a decade and a half to kind of internalize that was really an important idea. And I think, if it turns out we find the whole universe lurking out there in the computational universe, that's a good, it's a good brownie point or something for the whole idea. But I think that the thing that's strange in this whole question about, finding this different raw material for making models of things, what's been interesting sort of in the sort of arc of history is, for 300 years, it's kind of like the mathematical equations approach. It was the winner. It was the thing, you want to have a really good model for something, that's what you use. The thing that's been remarkable is just in the last decade or so, I think one can see a transition to using not mathematical equations, but programs as sort of the raw material for making models of stuff. Mm-hmm. And that's pretty neat. And it's kind of, as somebody who's kind of lived inside this paradigm shift, so to speak, it is bizarre. I mean, no doubt in sort of the history of science, that will be seen as an instantaneous paradigm shift. But it sure isn't instantaneous when it's played out in one's actual life, so to speak. Right. It seems glacial. And it's the kind of thing where it's sort of interesting because in the dynamics of sort of the adoption of ideas like that into different fields, the younger the field, the faster the adoption typically, because people are not kind of locked in with the fifth generation of people who've studied this field, and it is the way it is, and it can never be any different. And I think that's been, watching that process has been interesting. I mean, I think I'm fortunate that I do stuff mainly because I like doing it, and if I was, that makes me kind of thick-skinned about the world's response to what I do. Mm-hmm. But that's definitely, and any time you write a book called something like A New Kind of Science, it's kind of the pitchforks will come out for the old kind of science. And it was interesting dynamics. I think that I have to say that I was fully aware of the fact that when you see sort of incipient paradigm shifts in science, the vigor of the negative response upon early introduction is a fantastic positive indicator of good long-term results. So in other words, if people just don't care, it's that's not such a good sign. If they're like, oh, this is great, that means you didn't really discover anything interesting.
What fascinating properties of Rule 30 have you discovered over the years? You've recently announced the Rule 30 prizes for solving 3 key problems. Can you maybe talk about interesting properties that have been kind of revealed, Rule 30 or other cellular automata, and what problems are still before us, like the 3 problems you've announced?
Yeah, right. So, I mean, the most interesting thing about cellular automata is that it's hard to figure stuff out about them. And that's, in a sense, every time you try and sort of, you try and bash them with some other technique, you say, can I crack them? The answer is they seem to be uncrackable. They seem to have the feature that they are, that they're sort of showing irreducible computation. You're not able to say, oh, I know exactly what this is going to do. It's going to do this or that.
But there's specific formulations of that fact.
Yes, right. So, I mean, for example, in Rule 30, in the pattern you get just starting from a single black cell, you get this sort of very, very sort of random looking pattern. And so one feature of that, you just look at the center column. And for example, we used that for a long time to generate randomness in Wolfram language. What Rule 30 produces. Now, the question is, can you prove how random it is? So, for example, one very simple question, can you prove that it'll never repeat? No, we haven't been able to show that it will never repeat. We know that if there are 2 adjacent columns, we know they can't both repeat. But just knowing whether that center column can ever repeat, we still don't even know that. Another problem that I sort of put in my collection of, it's like $30,000 for 3, for these 3 prizes for about Rule 30. I would say that this is not one of those. This is one of those cases where the money is not the main point, but it's just helps motivate somehow the investigation.
So there's 3 problems you propose. You get $30,000 if you solve all 3, or maybe I don't know.
No, it's $10,000 for each.
For each, right?
Yeah.
The problems. That's right. Money's not the thing. The problems themselves are just clean.
Right.
Formulations.
So it's just will it ever become periodic? Second problem is, are there an equal number of black and white cells
down the middle column? And the third problem is a little bit harder to state, which is essentially, is there a way of figuring out what the color of a cell at position T down the center column is with a less computational effort than about T steps? So in other words, is there a way to jump ahead and say, I know what this is going to do. It's just some mathematical function of T. Or proving that there is no way.
Or proving there is no way, yes. But both, for any one of these, one could prove that, one could discover, we know what Rule 30 does for 1 billion steps, but, and maybe we'll know for 1 trillion steps before too very long. But maybe at 1 quadrillion steps, it suddenly becomes repetitive. You might say, how could that possibly happen? But so when I was writing up these prizes, I thought, and this is typical of what happens in the computational universe, I thought, let me find an example where it looks like it's just going to be random forever, but actually it becomes repetitive.
Yeah.
And I found one. And it's just, I did a search. I searched, I don't know, maybe 1 million different rules with some criterion. And this is, what's sort of interesting about that is I kind of have this thing that I say in a kind of silly way about the computational universe, which is, the animals are always smarter than you are. That is, there's always some way one of these computational systems is going to figure out how to do something, even though I can't imagine how it's going to do it. And, I didn't think I would find one that, you would think after all these years that when I found sort of all possible things, funky things that I would have gotten my intuition wrapped around the idea that, these creatures are always in the computational universe are always smarter than I'm going to be. But,
well, they're equivalently as smart, right?
That's correct. and that makes one feel very sort of, it's humbling every time, because every time the thing is, you think it's going to do this, or it's not going to be possible to do this. And it turns out it finds a way.
Of course, the promising thing is there's a lot of other rules like Rule 30. It's just Rule 30 is...
Oh, it's my favorite because I found it first. And
that's right. But the problems are focusing on Rule 30. It's possible that Rule 30 is repetitive after a trillion steps.
It is possible.
And that doesn't prove anything about the other rules.
It does not.
But this is a good sort of experiment of how you go about trying to prove something about a particular rule.
Yes. And it also, all these things help build intuition. That is, if it turned out that this was repetitive after a trillion steps, that's not what I would expect. And so we learned something from that.
The method to do that, though, would reveal something interesting about the cellular automata stuff.
No doubt. I mean, it's although it's sometimes challenging. Like I put out a prize in 2007 for a particular Turing machine that was the simplest candidate for being a universal Turing machine, and the young chap in England named Alex Smith, after a smallish number of months, said, "I've got a proof." And he did. It took a little while to iterate, but he had a proof. Unfortunately, the proof is it's a lot of micro details. It's not like you look at it and you say, aha, there's a big new principle. The big new principle is the simplest Turing machine that might have been universal actually is universal. And it's incredibly much simpler than the Turing machines that people already knew were universal before that. And so that intuitionally is important because it says, computational universality is closer at hand than you might have thought. But the actual methods are not, in that particular case, were not terribly illuminated.
It would be nice if the methods would also be elegant.
That's true. Yeah, no, I mean, I think it's one of these things where, it's like a lot of, we've talked about earlier, kind of, opening up AIs and machine learning and things of what's going on inside. Yeah. And is it just step by step, or can you sort of see the bigger picture more abstractly?
It's unfortunate. With Fermat's last theorem proof, it's unfortunate that the proof to such an elegant theorem is not. It's not. It doesn't fit into the margins of a page.
That's true. But one of the things is that's another consequence of computational irreducibility. This fact that there are even quite short results in mathematics whose proofs are arbitrarily long.
Yes,
that's a consequence of all this stuff, and it makes one wonder. How come mathematics is possible at all?
Right.
Why is it the case? How have people managed to navigate doing mathematics through looking at things where they're not just thrown into it's all undecidable? That's its own separate story.
And that would have a poetic beauty to it if people were to find something interesting about Rule 30, because there's an emphasis to this particular rule. It wouldn't say anything about the broad irreducibility of all computations, but it would nevertheless put a few smiles on people's faces of.
But to me, it's like, in a sense, establishing the principle of computational equivalence. It's a little bit like doing inductive science anywhere. That is, the more examples you find, the more convinced you are that it's generally true. We don't get to, whenever we do natural science, we say, well, it's true here that this or that happens. Can we prove that it's true everywhere in the universe? No, we can't. So, it's the same thing here. We're exploring the computational universe. We're establishing facts in the computational universe. And that's sort of a way of inductively concluding general things.
Just to think through this a little bit, we've touched on it a little bit before, but what's the difference between the kind of computation, now that we've talked about cellular automata, what's the difference between the kind of computation, biological systems, our mind, our bodies, the things we see before us that emerge through the process of evolution, and cellular automata? We've kind of implied through the discussion of physics underlying everything, but we talked about the potential equivalence of the fundamental laws of physics and the kind of computation going on in Turing machines. But can you now connect that? Do you think there's something special or interesting about the kind of computation that our bodies do?
Right. Well, let's talk about brains primarily.
Brains.
I think the most important thing about the things that our brains do are that we care about them, in the sense that there's a lot of computation going on out there,
right,
in cellular automata and physical systems and so on, and it does what it does. It follows those rules. It does what it does. The thing that's special about the computation in our brains is that it's connected to our goals and our kind of whole societal story. And, I think that's the special feature. And now the question then is, when you see this whole sort of ocean of computation out there, how do you connect that to the things that we humans care about? Mm-hmm. And in a sense, a large part of my life has been involved in sort of the technology of how to do that. And, what I've been interested in is kind of building computational language that allows that something that both we humans can understand and that can be used to determine computations that are actually computations we care about. See, I think when you look at something like one of these cellular automata and it does some complicated thing, you say, that's fun, but why do I care? Well, you could say the same thing actually in physics. You say, oh, I've got this material and it's a ferrite or something. Why do I care? It has some magnetic properties. Why do I care? It's amusing, but why do I care? Well, we end up caring because, ferrite is what's used to make magnetic tape, magnetic disks, whatever. Or, we could use liquid crystals used to make, well, not actually, increasingly not, but it has been used to make computer displays and so on. But so in a sense, we're mining these things that happen to exist in the physical universe and making it be something that we care about because we sort of entrain it into technology. And it's the same thing in the computational universe, that a lot of what's out there is stuff that's just happening, but sometimes we have some objective and we will go and sort of mine the computational universe for something that's useful for some particular objective. On a large scale, trying to do that, trying to sort of navigate the computational universe to do useful things, that's where computational language comes in. And, a lot of what I've spent time doing and building this thing we call Wolfram language, which I've been building for the last 1/3 of a century now. The goal there is to have a way to express kind of computational thinking, computational thoughts in a way that both humans and machines can understand. So it's kind of like in the tradition of computer languages, programming languages, that the tradition there has been more, let's take how computers are built and let's have a human way to specify, do this, do this, do this at the level of the way that computers are built. What I've been interested in is representing sort of the whole world computationally and being able to talk about whether it's about cities or chemicals or, this kind of algorithm or that kind of algorithm, things that have come to exist in our civilization and the sort of knowledge base of our civilization, being able to talk directly about those in a computational language so that both we can understand it and computers can understand it. I mean, the thing that I've been sort of excited about recently, which I had only realized recently, which is kind of embarrassing, but is kind of the arc of what we've tried to do in building this kind of computational language is it's a similar kind of arc of what happened when mathematical notation was invented. Mm-hmm. So go back 400 years, people were trying to do math. They were always explaining their math in words. And it was pretty clunky. And as soon as mathematical notation was invented, you could start defining things like algebra and later calculus and so on. It all became much more streamlined. When we deal with computational thinking about the world, there's a question of what is the notation? What is the kind of formalism that we can use to talk about the world computationally? And in a sense, that's what I've spent the last 1/3 of a century trying to build. And we finally got to the point where we have a pretty full-scale computational language that sort of talks about the world. And that's exciting because it means that just like having this mathematical notation let us talk about the world mathematically, we now, and let us build up these kind of mathematical sciences. Now we have a computational language which allows us to start talking about the world computationally and lets us, my view of it is it's kind of computational X for all X, all these different fields of, computational this, computational that. That's what we can now build.
Let's step back about just to backtrack a little bit about cellular automata. Being able to, what's it like to be a cellular automata in a way that's equivalent to what is it like to be a conscious human being? How do you approach that? So is it looking at some subset of the cellular automata, asking questions of that subset, like how the world is perceived, how you
something like
as that subset, Like for that local pocket of computation, what are you able to say about the broader
Something
cellular
like that.
And that somehow then can give you a sense of how to step outside of that cellular
Right,
automata.
but the tricky part is that little subset, what it's doing is it has a view of itself. And the question is, how do you get inside it? It's like, when with humans, right? It's like we can't get inside each other's consciousness. Mm-hmm. That doesn't really, that doesn't really even make sense. It's like there is an experience that somebody is having, but you can perceive things from the outside, but sort of getting inside it doesn't quite make sense. And for me, these sort of philosophical issues, and this one I have not untangled. So let's be
sure.
For me, the thing that has been really interesting in thinking through some of these things is, when it comes to questions about consciousness or whatever else, it's like when I can run a program and actually see pictures and, make things concrete, I have a much better chance to understand what's going on than when I'm just trying to reason about things in a very abstract way.
Yeah, but there may be a way to map the program to your conscious experience. So, for example, when you play a video game, you do a first-person shooter. Mm-hmm. You walk around inside this entity.
Yep.
It's a very different thing than watching this entity. So, if you can somehow connect more and more this full conscious experience to the subset of the cellular automata.
Yeah, it's something like that. But the difference in the first-person shooter thing is there's still your brain and your memory is still remembering. You still have. It's hard to. I mean, again, what one's going to get. One is not going to actually be able to be the cellular automaton. One's going to be able to watch what the cellular automaton does. But this is the frustrating thing that I'm trying to understand. How to think about being it, so to speak.
Okay, so like in virtual reality, there's a concept of immersion. Like with anything, with video game, with books, mm-hmm. there's a concept of immersion. It feels like over time, if the virtual reality experience is well done, and maybe in the future it'll be extremely well done, the immersion leads you to feel like you mentioned memories. You forget that you even ever existed outside that experience. Yeah. It's so immersive. I mean, you could argue sort of mathematically that you can never truly become immersed, but maybe you can. I mean,
well, yeah. I mean,
why can't you merge with the cellular automata?
Yeah, right.
I mean, aren't you just part of the same fabric? Why can't you just like?
Well, that's a good question. I mean, so let's imagine the following scenario. Let's imagine
can you return.
What's that? Well,
but then can you return back?
Well, yeah, right. I mean, it's like let's imagine you've uploaded. Your brain is scanned. You've got every synapse, mapped out. You upload everything about you, the brain simulator. You upload the brain simulator, and the brain simulator is basically, some glorified cellular automaton. Mm-hmm. And then you say, well, now we've got an answer to what does it feel like to be a cellular automaton? It feels just like it felt to be ordinary you, because they're both computational systems and they're both, operating in the same way. So in a sense, but I think there's somehow more to it, because in that sense, when you're just making a brain simulator, it's just, we're just saying there's another version of our consciousness. The question that we're asking is, if we tease away from our consciousness and get to something that is different, how do we make a bridge to understanding what's going on there? Mm-hmm. And, there's a way of thinking about this. Okay, so this is coming on to sort of questions about the existence of the universe and so on. Mm-hmm. But one of the things is there's this notion that we have of rulal space. Mm-hmm. So we have this idea of there's physical space, which is, something you can move around in that's associated with the extent of the spatial hypergraph. Then there's what we call branchial space, the space of quantum branches. So in this thing we call the multi-way graph of all of this sort of branching histories, mm-hmm. there's this idea of a kind of space where instead of moving around in physical space, you're moving from history to history, so to speak, from one possible history to another possible history. And that's kind of a different kind of space. That is the space in which quantum mechanics plays out. Mm-hmm. Quantum mechanics, like, for example, something like, I think we're slowly understanding things like destructive interference in quantum mechanics. That what's happening is branchial space is associated with phase in quantum mechanics. And what's happening is the two photons that are supposed to be interfering and destructively interfering are winding up at different ends of branchial space. And so us, as these poor observers, that have branching brains that are trying to conflate together these different threads of history and say, we've really got a consistent story that we're telling here. We're really knitting together these threads of history. By the time the two photons wound up at opposite ends of branchial space, we just can't knit them together to tell a consistent story. So for us, that's sort of the analog of destructive interference.
Got it. And then there's rulal space too, which is the space of rules.
Yes, well, that's another level up. So there's the question. Actually, I do want to mention one thing because it's something I've realized in recent times, and I think it's really, really kind of cool, which is about time dilation and relativity, and it kind of helps to understand. It's something that kind of helps in understanding what's going on. So, according to relativity, if you have a clock, it's ticking at a certain rate. You send it in a spacecraft that's going at some significant fraction of the speed of light. To you as an observer at rest, that clock that's in the spacecraft will seem to be ticking much more slowly. And so, in other words, it's kind of like the twin who goes off to Alpha Centauri and goes very fast will age much less than the twin who's on Earth that is just hanging out where they're hanging out. Mm-hmm. Okay, why does that happen? Okay, so it has to do with what motion is. So in our models of physics, what is motion? Well, when you move from somewhere to somewhere, you're having to sort of recreate yourself at a different place in space. Mm-hmm. When you exist at a particular place and you just evolve with time, you're updating yourself, you're following these rules to update what happens. Well, so the question is, when you have a certain amount of computation in you, so to speak, when there's a certain amount, you're computing, the universe is computing at a certain rate, you can either use that computation to work out, sitting still where you are, what's going to happen successively in time, or you can use that computation to recreate yourself as you move around the universe. Mm-hmm. And so time dilation ends up being, it's really cool actually that this is explainable in a way that isn't just imagine the mathematics of relativity. Mm-hmm. But that time dilation is a story of the fact that as you kind of are recreating yourself as you move, you are using up some of your computation. And so you don't have as much computation left over to actually work out what happens progressively with time. Mm-hmm. So that means that time is running more slowly for you because it is you're using up your computation. Your clock can't tick as quickly because every tick of the clock is using up some computation, but you already used that computation up on moving at half the speed of light or something. And so that's why time dilation happens. And so you can start. So it's kind of interesting that one can sort of get an intuition about something like that because it has seemed like just a mathematical fact about the mathematics of special relativity and so on.
Well, for me, it's a little bit confusing what the you in that picture is because you're using up computation.
Okay, so we're simply saying the entity is updating itself according to the way that the universe updates itself. Mm-hmm. And the question is, those updates, let's imagine the U as a clock, mm-hmm. Okay? And the clock is, there's all these little updates, the hypergraph, and a sequence of updates cause the pendulum to swing back the other way and then swinging back and forth, okay? And all of those updates are contributing to the motion of the pendulum going back and forth or the little oscillator moving, whatever it is, okay? But then the alternative is that's sort of situation one where the thing is at rest. Situation two, where it's kind of moving, what's happening is it is having to recreate itself at every moment. Mm-hmm. The thing is going to have to do the computations to be able to sort of recreate itself at a different position in space. And that's kind of the intuition behind. So it's either going to spend its computation recreating itself at a different position in space, or it's going to spend its computation doing the doing the updating of the ticking of the clock, so to speak.
Mm-hmm. So the more updating is doing, the less the ticking of the clock update is doing. That's
right. The more it's having to update because of motion,
yeah,
the less it can update the clock. So that's obviously there's a sort of mathematical version of it that relates to how it actually works in relativity. But that's kind of, to me, that was sort of exciting to me that it's possible to have a really mechanically explainable story there. that isn't, and it's similarly in quantum mechanics, this notion of branching brains, perceiving branching universes, to me, that's getting towards a sort of mechanically explainable version of what happens in quantum mechanics, even though it's a little bit mind-bending to see, these things about under what circumstances can you successfully knit together those different threads of history, and when do things sort of escape, and those kinds of things. But the thing about this physical space, the main sort of big theory is general relativity, the theory of gravity, and that tells you how things move in physical space. In branchial space, the big theory is the Feynman path integral, which it turns out tells you essentially how things move in the space of quantum phases. So it's kind of like motion in branchial space. And it's kind of a fun thing to start thinking about all these things that we know in physical space, like event horizons and black holes and so on. What are the analogous things in branchial space? For example, the speed of light. What's the analog of the speed of light in branchial space? It's the maximum speed of quantum entanglement. So the speed of light is a flash bulb goes off here. What's the maximum rate at which the effect of that flash bulb is detectable moving away in space? So similarly, in branchial space, something happens, and the question is, how far in this branchial space, in the space of quantum states, how far away can that get within a certain period of time? And so there's this notion of a maximum entanglement speed, and that might be observable. That's the thing we've been sort of poking at, is might there be a way to observe it even in some atomic physics kind of situation? Because one of the things that's weird in quantum mechanics is when we study quantum mechanics, we mostly study it in terms of small numbers of particles. This electron does this thing on an ion trap does that, and so on. But when we deal with large numbers of particles, kind of all bets are off. It's kind of too complicated to deal with quantum mechanics. And so what ends up happening is, so this question about maximum entanglement speed and things like that may actually play in one of these, in the sort of story of many-body quantum mechanics. And I even have some suspicions about things that might happen even in, one of the things I realized I'd never understood, and it's kind of embarrassing, but I think I now understand a little better, is when you have chemistry and you have quantum mechanics, it's like, well, there's two carbon atoms as this molecule, and we do a reaction, and we draw a diagram, and we say this carbon atom ends up in this place. And it's like, but wait a minute. In quantum mechanics, nothing ends up in a definite place. There's always just some wave function for this to happen. How can it be the case that we can draw these reasonable, it just ended up in this place? And you have to kind of say, well, the environment of the molecule effectively made a bunch of measurements on the molecule to keep it kind of classical. And that's a story that has to do with this whole thing about measurements have to do with this idea of, can we conclude that something definite happened? Because in quantum mechanics, the intrinsic quantum mechanics, the mathematics of quantum mechanics is all about, they're just these amplitudes for different things to happen. Then there's this thing of, and then we make a measurement and we conclude that something definite happened. And that has to do with this thing, I think, about sort of about knitting together these different threads of history and saying, this is now something where we can definitively say something definite happened. In the traditional theory of quantum mechanics, it's just like, after you've done all this amplitude computation, then this big hammer comes down and you do a measurement and it's all over. And that's been very confusing. For example, in quantum computing, it's been a very confusing thing because when you say, in quantum computing, the basic idea is you're going to use all these separate threads of computation, so to speak, to do all the different parts of, try these different factors for an integer or something like this. And it looks like you can do a lot because you've got all these different threads going on. But then you have to say, well, at the end of it, you've got all these threads and every thread came up with a definite answer, but we got to conflate those together to figure out a definite thing that we humans can take away from it, so the computer actually produced this output.
You mentioned something about, do cellular automata exist outside the human mind in our little offline conversation? Why is that an interesting question? So cellular automata, complexity, what's the relationship between complexity and the human mind and trees falling in the forest?
Infrastructure. So the CA, so when John von Neumann and Conway and Feynman were doing CAs, were doing on paper.
CA is cellular automata.
Yeah, just drawing them on paper.
How awesome is that they were doing cellular automata on paper?
Yeah.
And then they were doing a computer that takes like forever to print out anything and program.
Sure.
People are not with the TikTok, kids these days with the TikTok, don't understand how amazing it is to just play with Cellular Automata, arbitrarily changing the rules as you want, the initial conditions, and see the beautiful patterns emerge. Same with fractals, all of that.
You've just given me a brilliant idea. I wonder if there's a TikTok account that's just dedicated to putting out CA rules, and if it isn't, we should make one.
100%. And that will get
So we have millions of views. I mean, like
millions. Yes, no, it'll get dozens.
or just have it running. So look, I kind of CA. I love CAs. Sorry.
Yeah, no,
We just have to make one. I actually a few years ago I made some robots that talked to each other, chemical robots that played the game of Hex, invented by John Nash, by doing chemistry, and they communicated via Twitter, which experiments they were doing. And they had a lookup table of experiments. And robot one said, "I'm doing experiment 10." And the other robot, "Okay, I'll do experiment 1 then."
And they communicated
via Twitter, and then
publicly or DMs.
Yeah.
Can you maybe quickly explain what the game of Hex is?
So it's basically a hexagonal board, and you try and basically you color each element on the board, each hexagon, and you try and get from one side to the other, and the other one tries to block you.
Wait, how are they connected?
So what the robots?
It's a chemical.
Let's go back. So the two robots.
Yeah.
Each robot was doing dye chemistry, so making RGB, red, green, blue, red, green, blue, red, green, blue, and they could just choose from experiments to do red, green, blue. Initially, I said to my group, "We need to make 2 chemical robots that play chess," and my group were like, "That's too hard. No,
too complicated.
Go away." But anyway, so we had the robot.
By the way, people listening to this should probably know that Lee Cronin is a amazing group of brilliant people. He's exceptionally well published. He's written a huge number of amazing papers. Whenever he calls himself stupid and is a sign of humility, and I deeply respect that and appreciate it. So people listening to this should know this is a world-class scientist who doesn't take himself seriously, which I really appreciate and love. Anywho, talking about serious science, we're back to your group rejecting your idea of chemical robots playing chess via dyes. So you went to a simpler game of Hex. Okay, so what else?
The team that did it were brilliant. I really take I think they still have PTSD from doing it, because I said this is a workshop. What I'd often do is I have about 60 people on my team, and occasionally before lockdown I would say, "I'm a bit bored. We're gonna have a workshop on something. Who wants to come?" And then basically about 20 people turn up to my office, and I say, "We're gonna do this mad thing," and then it would just self-organize, and some of them would be like, "No, I'm not doing this," and then you get left with the happy dozen.
Yeah.
And what we did is we built this robot, and doing dye chemistry is really easy. You can just take 2 molecules, react them together, and change color. And what I wanted to do is have a palette of different molecules. You could react combinatorially and get different colors. So you got 2 robots. And I went, wouldn't it be cool if the robots basically shared the same list of reactions to do? And they said, because then you could do a kind of multi-core chemistry. Like they weren't, so you could have 2 chemical reactions going on at once, and they could basically outsource the problem.
But they're sharing the same tape.
Exactly.
Okay.
So robot 1 would say, I'm going to do experiment 1, and the other robot says, I'll do experiment 100. And then they cross it off. But I wanted to make it
That's brilliant, by the way. That is genius. Sorry.
Well, yeah. I wanted to make it groovier, and I said, look, let's have them competing.
Yeah.
So they're playing a game of Hex, and so when the robot does an experiment, and the more blue the die, the more it gets the higher chance it gets to make the move it wants on the hex board. So if it gets a red color, is like it gets downweighted in the other robot. And so what the robots could do is they each play a move, and because the fitness function or the optimization function was to make the color blue, they started to invent reactions weren't on the list, and they did this by not cleaning, because we made cleaning optional. So when one robot realized if it didn't clean its pipes, it could get blue more quickly.
Yeah.
And the other robot realized that, so it was like getting dirty as well. And they
unintended consequences of superintelligence. Okay. But
that was the game. And we
communicating through Twitter, though.
They were doing it through Twitter, and Twitter banned them a couple of times. I said, come on, you've got a couple of robots doing chemistry. It's really cool. Stop banning them.
Yeah.
But in the end, we had to take them off Twitter, and they just communicated via a server, because it was just, there were people saying, you can still find it, Cronin Lab 1 and Cronin Lab 2 on Twitter. And it was like, make, move, wait, mix A and B, wait 10 seconds, answer blue,
I really find it super compelling that you would have a chemical entity that's communicating with the world.
That was one of the things I want to do with my origin of life reaction, right? Is basically have a reactor that's basically just randomly enumerating through chemical space and have some kind of cycle, and then read out what the molecule's reading out using a mass spectrometer, and then convert that to text and publish it on Twitter, and then wait until it says I'm alive. I reckon that Twitter account will get a lot of followers.
Yeah.
And I'm still trying to convince my group that we should just make an Origin of Life Twitter account where it's going blah, 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 and it's like, hello, testing.
Yeah.
I'm here.
Well, I'll share it. I like it. I particularly enjoy this idea of a non-human entity communicating with the world via a human-designed social network. It's quite a beautiful idea. How we were talking about CAs existing outside the human mind.
Yeah. So I really admire Stephen Wolfram. I think he's a genius, clearly a genius. And trapped in is like a problem with being so smart is you get trapped in your own, mind, right? And I tried to convince Stephen that assembly theory wasn't nonsense. He was like, no, it's just nonsense. I was a little bit sad by that.
So nonsense applied, even if it applied to the simplest construct of a one-dimensional cellular automata, for example.
Yeah. But I mean, actually, maybe I'm doing myself a bit too down. It was just as the theory was coming through, and I didn't really know how to explain it. Mm-hmm. But we are going to use assembly theory in CAs in cellular automata. But what I was really curious about is why people marvel. I mean, you marvel at CAs and their complexity, and I said, well, hang on, that complexity is baked in, because if you play the game of life in a CA, you have to run it on a computer. Yeah. You have to do a number of operations, put in the boundary conditions. So is it surprising that you get this structure out? Is it manufactured by the boundary conditions? And it is interesting because I think cellular automata running them is teaching me something about what real numbers are and aren't. And I haven't quite got there yet. I was playing on the airplane coming over and just realized I have no idea what real numbers are, really. And I was like, well, I do actually have some notion of what real numbers are. And I think thinking about real numbers as functions rather than numbers is more appropriate. And then if you then apply that to CAs, then you're saying, well, actually, why am I seeing this complexity in this rule? Is it you've got this deterministic system, and yet you get this incredible structure coming out. Mm-hmm. Well, isn't that what you'd get with any real number as you apply it as a function, and you're trying to read it out to an arbitrary precision? And I wonder if CAs are just helping me. Well, my misunderstanding of CAs might be helping me understand them in terms of real numbers. I don't know what you think.
Yeah, well, the devil's in the function.
Mm-hmm.
Like, which is the function that's generating your real number? Like that, it seems like it's very important, the specific algorithm of that function, because some lead to something super trivial, some lead to something that's all chaotic, and some lead to things that are just walk that fine line of complexity and structure.
I think we agree. So let's take it back a second. So take the logistic map or something, logistic equation, where you have this equation, which is you don't know what's going to happen at n+1, but once you've done n+1, you know for all time. You can't predict it. For me, CAs and logistic equation feel similar, and I think what's incredibly interesting, and I share your kind of wonder at running a CA, but also I'm saying, well, what is it about the boundary conditions and the way I'm running that calculation? So in my group, with my team, we actually made a chemical CA. We made Game of Life. We actually made a physical grid. I haven't been able to publish this paper. It's been trapped in purgatory for a long time. But
you wrote it up as a paper, how to do a chemical formulation of the Game of Life.
We made a chemical computer and little cells.
And I was playing Game of Life.
With the BZ reactions. Each cell would pulse on and off, on and off, on and off. Yeah. We have little stirrer bars and we have little gates.
Yeah.
And we actually played Conway's Game of Life in there. And we got structures in that. We got structures in that game from the chemistry that you wouldn't expect from the actual CA. Mm-hmm. So that's kind of cool in that
because they were interacting outside of the cells somehow. Or
so what's happening is you're getting noise. So the thing is, You've got this BZ reaction that gives on, off, on, off, on, off, but there's also a wake. And those wakes constructively interfere and in such a non-trivial way that's non-deterministic. And the non-determinism in the system gives very rich dynamics. And I was wondering if I could physically make a chemical computer with this CA that gives me something different that I can't get in a silicon representation of a CA where all the states are clean, because you don't have the noise trailing into the next round. You just have the state.
So the paper in particular, it's just a beautiful idea to use a chemical computer to construct a cellular automata, and the famous one of Game of Life. But it's also interesting, and it's a really interesting scientific question of whether some kind of random perturbations or some source of randomness can have a significant constructive effect on the complexity of the system.
And indeed, I mean, whether it's random or just non-deterministic, and can we bake in that non-determinism at the beginning? I wonder what is I'm trying to think about what is the encoding space. The encoding space is pretty big. We have 49 stirrups of 49 cells, 49 chem bits, all connected to one another in like an analog computer, but being read out discretely as the BZ reaction. So just to say, the BZ reaction is a chemical oscillator. And what happened in each cell is it goes between red and blue. So two Russians discovered it, Belousov, Zabotinsky. I think Belousov first proposed it, and everyone said, you're crazy, it breaks the second law. And Zabotinsky said, no, it doesn't break the second law, it's consuming a fuel. And it's there's a lot of chemistry hidden in the Russian literature, actually. Just because Russians just wrote it in Russian, they didn't publish it in English-speaking journals.
It's heartbreaking, actually.
Well,
but
it's sad, and it's great that it's there, right? It's not lost. I'm sure we will find a way of translating it properly.
Yeah. Well, the silver lining / greater sadness of all of this is there's probably ideas in English speaking, like there's ideas in certain disciplines that, if discovered by other disciplines, would crack open some of the biggest mysteries in those disciplines. Like computer science, for example, is trying to solve problems like nobody else has ever tried to solve problems.
Yeah.
as if it's not already been all addressed in cognitive science, in psychology, in mathematics, in physics, in just whatever you want to, economics even. But if you look into that literature, you might be able to discover some beautiful ideas. Obviously, Russian is an interesting case of that because there's a loss in translation. But you said there's a source of fuel, a source of energy.
Yeah. So the BZ reaction, you have an acid in there called malonic acid.
Yeah.
And what happens is it's basically like a battery that powers it. And it loses CO2, so decarboxylates. It's just a chemical reaction. What that means we have to do is continuously feed, or we just keep the BZ reaction going in a long enough time, so it's like it's reversible in time.
But only like.
Only like. But it's fascinating. I mean, the team that did it, I'm really proud of their persistence. We made a chemical computer. It can solve little problems. It can solve traveling salesman problems, actually.
Nice.
But like I say, it's
but not any faster than a regular computer. Is there something you could do?
Maybe. I'm not sure. I'm not. I think we can come up with a way of solving problems, also really complex, hard ones, because it's an analog computer, and it can energy minimize really quickly. It doesn't have to basically go through every element in the matrix, like and flip it. It just reads out. So we could actually do Monte Carlo by just shaking the box. It's literally a box shaker. You don't actually have to encode the shaking of the box in a silicon memory and then just shuffle everything around. Yeah, and
it's analog, it's natural, so it's an organic computer.
Yeah. So I was playing around with this, and I was kind of annoying some of my colleagues and wondering if we could get to chemical supremacy, like quantum supremacy. And I kind of calculated how big the grid has to be so we can actually start to solve problems faster than a silicon computer. Mm-hmm. But I'm not willing to state how that is yet, because I'm probably wrong. It's not that it's any top secret thing. I think I can make a chemical computer that can solve optimization problems faster than a silicon computer.
That's fascinating. But then you're unsure how big that has to be.
Yeah, I think. I mean,
It might be a big box, hard to shake. I don't
it
know.
might be exactly a big box, hard to shake, and basically a bit sloppy.
Did we answer the question about do cellular automata exist outside the mind?
We didn't, but I would posit that they don't, but I think minds can. Well,
So the mind is fundamental.
what
What's the
I
why?
sorry, so let's just go back. So, as a physical phenomena, do CAs exist in physical reality? Right? I would say they probably don't exist outside the human mind, but now I've constructed them. They exist in computer memories. They exist in my lab. They exist on paper. So they emerge from the human mind. I'm just interested in, because Stephen Wolfram likes CAs, a lot of people like CAs, and likes to think of them as minimal computational elements. I'm just saying, well, do they exist in reality, or are they a representation of a simple machine that's just very elegant to implement?
So it's a platonic question, I guess.
Yeah.
I mean, it's there's initial conditions, there's a memory in the system, there's simple rules that dictate the evolution of the system. So what exists? The idea, the rules, the
Yeah, people are using CAs as models for things in reality to say, hey, look, you can do this thing in a CA. And my when I see this, I'm saying, oh, that's cool, but what does that tell me about reality? Where's the CA in space time?
Oh, I see. Well,
Yeah.
right. It's a mathematical object. So for people who don't know cellular automata, there's usually a grid, whether it's one-dimensional, two-dimensional, or three-dimensional, and it evolves by simple local rules, like you die or are born if the neighbors are alive or dead. And it turns out if you have with certain kinds of initial conditions and with certain kinds of very simple rules, you can create like arbitrarily complex and beautiful systems. And to me, whether drugs are involved or not, I can sit back for hours and enjoy the mystery of it, how such complexity can emerge. It gives me almost like, people talk about religious experiences. It gives me a sense that you get to have a glimpse at the origin of this whole thing.
Mm-hmm.
Whatever is creating this complexity from such simplicity is the very thing that brought my mind to life. This me, the human, our human civilization. And yes, those constructs are pretty trivial. That's part of their magic, is even in this trivial framework, you could see the emergence, or especially in this trivial framework, you could see the emergence of complexity from simplicity. I guess what Lee, you're saying is that this is not, this is highly unlike systems we see in the physical world, even though they probably carry some of the same magic, like mechanistically.
I'm saying that the operating system that a CA has to exist on is quite complex.
Right.
And so I wonder if you're getting the complexity out of the CA from the boundary conditions of the operating system, the underlying digital computer.
Oh, wow. So those are some strong words against CAs then. I didn't realize.
Not against. I'm in love with CAs as well.
Right.
I'm just saying they aren't as trivial as people think. They are incredible.
Yeah.
To get to that richness, you have to iterate billions of times, and you need a display, and you need a math coprocessor, and you need a von Neumann machine based on a Turing machine with digital error correction and states.
Wow. To think that for the simplicity of a grid, you're basically saying a grid is not simple.
Yeah.
It requires incredible complexity to bring a grid to life.
Yeah. Yeah, that's
then what is simple?
That's all I wanted to say. I agree with you with the wonder of CAs. I just think, but remember this: we take so much for granted what the CA is resting on, because von Neumann and Feynman weren't seeing these elaborate structures. They could not get that far.
Yeah, but that's the limitation of their mind.
That's exactly the limitation of their pencil.
But I think that's the question is whether the essential elements of the cellular automata is present without all the complexities required to build a computer.
And
My intuition, the reason I find it incredible is that, my intuition is yes. It might look different. There might not be a grid-like structure, but local interactions operating under simple rules and resulting in multi-hierarchical complex structures feels like a thing that doesn't require a computer.
I agree. But coming back to von Neumann and Feynman and Wolfram, their minds, the non-trivial minds, to create those architectures and do it, and to put on those state transitions. And I think that's something that's really incredibly interesting, that is understanding how the human mind builds those state transition machines.
I could see how deeply in love with the idea of memory you are. So it's like, how much of E equals mc squared, like, is more than an equation. It has Albert Einstein in it.
Mm-hmm.
Like, you're saying, like, you can't just say this is like, the equations of physics are a really good, simple capture of a physical phenomena. It is also has that equation has the memory of the humans.
Absolutely, yeah.
But I don't know if you're implying this. That's a beautiful idea, but I don't know if I'm comfortable with that sort of diminishing the power of that equation.
No, it
because
enhances
it's built
it.
on the shoulders. It enhances
I
it.
think it enhances it. It's not, that equation is a minimal compressed representation of reality, right?
Yeah.
We can use machine learning or Max Tegmark's AI Feynman to find lots of solutions for gravity. But isn't it wonderful that the laws that we do find are the maximally compressed representations?
Yeah, but that representation, you can now give it as, I guess the universe has the memory of Einstein with that representation, but then you can now give it as a gift for free.
Yeah,
to
it's
other
low
alien
memory.
civilizations.
Einstein had to go through a lot of pain to get there, but it's low memory. So I say that physics and chemistry and biology are the same discipline. They're just physics, laws in physics. There's no such thing as a law in physics. It's just low memory stuff. Because you've got low memory stuff, things reoccur quickly.
Mm-hmm.
As you build in more memory, you get to chemistry, so things become more contingent. When you get to biology, more contingent still, and then technology. So the more memory you need, the more your laws are local.
Mm-hmm.
That's all I'm saying. And that the less memory, the more the laws are universal, because they're not laws; they are just low memory states.